All right, before we begin, there are two things that I want to remind you of for watching a video to learn. And the two very, very important things that you will need to remember is the pause button and the rewind button. I do not leave any time in this video for you to write down and catch up to me. And as you know, I write pretty quickly. So you must pause the video so that you can write down the notes and keep up and listen as you go. And the second is the rewind. If you're trying to keep up and you miss what I say, or I talked really fast and you just need to hear it again, rewind the video. As a reminder, you are not watching this for fun. You are watching this to learn. Another strategy that I've had students use in the past is to watch the video twice. So the first time you watch the video, you just watch it and you see what I'm doing and you soak it in and you listen to everything that I say. And then the second time you are taking the notes and hearing it again and processing it again. So those are two strategies that you can use to be successful learners from a video. All right, are you guys ready to start our first distance learning video? I'm sure you're super excited. All right, so what we're taking a look at in this section is bases other than E. So far this unit, we have been looking at natural log, which is a log base E, and we have been looking at the exponential base E. Now we're going to take a look at what happens when we do not have a base E. So first of all, I'm going to give you a couple of definitions, one of which you should be fairly familiar with, and the second one, hopefully I can quickly help you to understand where this is coming from. The first one is an exponential. So we have this a to the x, and the definition is that it is equivalent to e to the x times natural log of a. And you may be wondering, where in the world did that come from? I'm going to reorganize this as e to the natural log of a times x. Well, what's e to the natural log of a? What does an exponential base e do to a log base e? They are inverses. They cancel each other out, leaving us with a, and that x is still in the exponent. The a becomes the base, and the x is the exponent. I just realized I did an entire simplifying an expression with no equal signs. Sorry about that. So each of those are equivalent expressions. Hopefully that helps you to understand where that definition comes from. The second definition is actually just a different way of writing that change of base formula that we used in pre-calculus. So log base a of x equals log of x, any new base, divided by log of the base, okay? So log of the input goes in the numerator, log of the base goes in the denominator. They just wrote these as a coefficient. As a reminder, all of this is a number. A is a number, so there's a numeric base. So 1 over the natural log of a is a number, so they just wrote it as a coefficient times natural log of x. All right, so we're going to use those definitions to find the derivative of a to the u and natural log base a of u. Notice this is a u, and we are taking the derivative with respect to x. So there will be a chain rule piece as we do this. So first of all, we are going to rewrite this with that definition, which was e to the natural log of a times u. Again, keeping that power the same. We know the derivative of e to the u, which is e to the u. In this case, we've got e to the natural log of a times u. Now, as a reminder, that a is a number. So natural log of a is a number. It's like a coefficient for u. So when we multiply by the derivative of the exponent, that natural log of a is a coefficient for the derivative of u. We're taking the derivative with respect to x. So it's that du dx piece. And then we're going to clean it up. As a reminder, this first piece here, this e to the natural log of a times u, that was the definition of a to the u times natural log of a, and then either times that du dx, or if you want to clean it up a little bit, u prime. Really, this last piece here is just indicating chain rule. If you do not just have regular plain old a to the x, you will have that chain rule piece. All right, now we're going to take the derivative of log base a of u. So we're going to rewrite it with that change of base formula, which was 1 over natural log of a, that base. Notice that the base is lower in log base a of u, so it goes in the denominator, and then times natural log of u. Again, as we take the derivative, that 1 over natural log of a, that is a number. It's a coefficient, so it just goes along as we take the derivative. That's an a. And we've got natural log of u, but we're taking the derivative with respect to x. So derivative of natural log is 1 over what you're taking the log of, and then we've got that chain rule piece, du dx. So we'll clean this up just a little bit. I'm going to put 1 over u times the natural log of a all together, and then you can have that du dx or u prime. The book will write it with that u prime in the numerator, and then u natural log of a in the denominator. All right, before we get started on using those derivatives, we're going to review some of our log properties. So evaluating log base 3 of 1/9. Remember curly law, 3 to what power will give me 1 over 9? Well, I know 3 squared is 9, so how does it end up in the denominator? And that happens when you have a negative exponent, so this would be -2. Second one, we're looking at finding the base, but we're going to think the same thing. What raised to the 1/3 power gives me an answer of 3? So this one I'm actually going to rewrite in exponential form. And then I'm going to go ahead and rewrite that 1/3 power as a cube root, because we're more familiar with roots than we are with rational exponents. So the cube root of what gives me 3? Well, I can solve this. I can cube both sides, but I also, in this case, can number sense it, and I know that the cube root of 27 is 3. Now we're going to take a look at solving an exponential equation. So this one might look really ugly to begin with, but notice everything inside those parentheses, those are all numbers. So if you really wanted to, you could punch that in your calculator and get a decimal approximation to start with. In order to get the variable out of the exponent, we need to use logs. So you could undo this using curly law, but again, this base is not the prettiest base you've ever seen. So you can also just take the log of both sides. All right, and then we can use properties of logs and make that exponent into a coefficient. So 12t times natural log of 1 plus 0.09 all over 12 equals, we haven't done anything to the right-hand side. And then to get t alone, we're going to be dividing by everything that's not t. We have 12 times t times natural log of 1 plus 0.09 over 12. It's all multiplication. So I'm going to cancel everything that is not my t with division. That is a 12. Sorry, my handwriting is not very pretty to begin with, and on a tablet it's even worse. So golden rule, whatever we do to one side, do the same thing to the other. And then we just punch this super fun expression into our calculator to get a decimal approximation. And I got about 12.253. All right, so that was it for review. Now we're going to use those new derivative laws to differentiate when we have a base that is not e. All right, so taking the derivative of both sides, dy dx, and derivative of an exponential that does not base e is going to be natural log of the base times the exponential itself, very similar to the derivative of e to the x is e to the x, and then times chain rule, that derivative of the power. So the derivative of negative 4x would be negative 4. And then I would clean that up a little bit. Negative 4 and natural log of 5 are both numbers. So I'm just going to multiply those together. And then we've got our 5 to the negative 4x power. All right, our next example, we have product rule. We have t squared, which is our first function, times 2 to the t, which is our second function. So g prime of t will equal 1 d2. So we're going to take the derivative of that 2 to the t. So we've got natural log of the base times the exponential 2 to the t power. And then in this case, there is no chain rule. So there's our 1 d2, add 2, that second function was 2 to the t, times the derivative of the first. Derivative of t squared is 2t. We're going to clean it up just a little bit. We've got t squared times 2 to the t times natural log of 2. And then over here, I'm just going to go ahead and write my 2t first. 2t times 2 to the t power. And finally, we're going to take the derivative of a log. All right, this one is a little bit less fun. Taking the derivative of a log. First of all, it will be 1 over natural log of the base. So our base is 3 times, thinking about the derivative of natural log, it is 1 over what you're taking the log of. So we've got that x squared minus 3x times chain rule, the derivative of what's inside. So the derivative of x squared is 2x. The derivative of negative 3x is negative 3. So notice the only difference between the derivative of this log and the derivative of natural log is this extra piece right here, that 1 over natural log of the base. Everything else is the same as the derivative of the natural log. All right, cleaning this up a little bit, we've got 2x minus 3 in the numerator, all over that natural log of 3 times x squared minus 3x. All right, as always, let me know if you have any questions.